A Morning at the Particle Zoo, or Sakata Model Revisited by Eugene Stefanovich. Chances are you saw this table, which is supposed to tell what our world is made of. Today we will be talking about the part highlighted by the red line. These are quarks and gluons, ingredients of the quark model that was invented by Gell-Mann and Zweig in 1964 in order to explain the inner structure of strongly interacting particles. For simplicity, we'll focus only on four types of quarks: up, down, strange, and charmed. This sector of the standard model was studied the best. The first surprising fact about quarks is that they cannot be observed. We can only see their bound states, which can be of two types: baryons and mesons. The formal distinction is that baryons have half-integer spin, 1/2, 3/2, etc., while mesons have integer spin of 0, 1, 2, and so on. Baryons, such as proton and neutron, are made of three quarks. Inside a proton, there are two up quarks and one down quark. Neutron's quarks are one up and two downs. The second funny thing about quarks is that they have fractional charges of 1/3 and 2/3. But these charges always add up in such a way that the total charge of the baryon is integer. In the case of proton, we have 2/3 plus 2/3 minus 1/3 equal to 1. In the case of neutron, the total charge is 0. Mesons are always made of one quark and one antiquark. The oldest are pi mesons, discovered in 1947. They come in three species: pi plus, pi 0, and pi minus. Their quark compositions are shown here. Don't be surprised that pi 0 meson is a sum of two states. This is quantum mechanics, where superpositions of states are permitted. Making all possible combinations of quark triples and quark-antiquark pairs, one can construct dozens of baryons and mesons and predict their properties. Almost all of these particles were found in nature. So the quark model is regarded as a huge success of modern theoretical physics. As we already mentioned, quarks cannot be observed in a free state outside of baryons and mesons. In 1960s and 1970s, lots of experimental efforts were spent on trying to find evidence of fractional charges, but without any success. Eventually, experimentalists agreed that this is impossible and gave up. The theory explains that this is a result of the so-called quark confinement. Suppose that you want to extract an up quark from a proton. While pulling the quark out, you have to do work against gluon forces that keep the proton quarks together. The gluon field extends like a piece of chewing gum, and the energy of the gluon string grows to the point where it is high enough to create a quark-antiquark pair. In my example, this is a down-anti-down pair. The chewing gum snaps, the down quark returns back to the original baryon, and the anti-down gets attached to the up quark that we tried to extract. So instead of getting a free up quark, we ended up with a neutron and a pi plus meson. Currently, the quark model is regarded as a cornerstone of the standard model and quantum chromodynamics. However, one may express a reasonable doubt about this model. As I have said above, quarks have not been seen directly. Yes, there are experiments like the deep inelastic scattering, which are explained nicely by the quark hypothesis, but they do not constitute a 100% proof. Gluons also have not been observed directly. No traces were found of fractional charges or the color quantum number. All these facts are usually explained by the confinement, but the mechanism of confinement is not well understood theoretically. And in general, equations of quantum chromodynamics are very difficult to solve, especially in the low energy regime, which is pertinent to the meson and baryon structures. There is no ironclad proof for the quark model. We may be excused for unleashing our imagination and thinking about alternative ways to explain the diversity of species in the subatomic zoo. Even before the advent of the quark model, people proposed ideas about what baryons and mesons can be made of. The most intriguing was the Fermi-Young model, published in 1949, just 2 years after the experimental discovery of pi mesons. Fermi and Young hypothesized that there are 4 truly elementary strongly interacting particles: proton, neutron, antiproton, and antineutron. Then pions could be explained as bound states of nucleons and antinucleons. Let's take, for example, proton and antineutron. When they are far from each other, the total mass is equal to the sum of proton mass plus neutron mass, 1878 mega electron volts. But suppose that there is a very strong attraction potential between these two particles, so that a bound state can be formed. A huge negative interaction energy is added to the sum of particle masses and reduces the total sum almost to zero, more precisely to 140 mega electron volts, which is the mass of the pi plus meson. Similarly, the pi 0 and pi minus could be also explained as nucleon-antinucleon bound states. While theoreticians perfected their models, experimentalists kept discovering more and more new particles. They were called strange particles, and they did not fit into the simple Fermi-Young scheme. In addition to new mesons, there were also new baryons, such as lambda, sigma, and psi. To cope with these developments, Shoichi Sakata in 1956 suggested to extend the Fermi-Young model. First, in addition to the two elementary baryons, proton and neutron, he added a third one, the strange lambda particle. In memory of Sakata, I'll call these 3 elementary particles the Sakatons. New mesons were built by the old Fermi-Young scheme. For example, K- meson is a bound state of lambda and antiproton. then new baryons could be described as three particle bound states made of two Sakatons and one anti-Sakaton. For example, sigma minus is composed of lambda, neutron, and antiproton. But the binding forces in three Sakaton baryons become a bit more complicated than in mesons. Let us consider a hypothetical particle consisting of a proton, a neutron, and an antineutron. Now, in addition to the Sakaton-anti-Sakaton attraction shown by green lines, we have a new type of force shown by the red line between the proton and the neutron. Actually, this force is very well known in nuclear physics. This interaction is responsible for the binding between nucleons when they form atomic nuclei. A typical nucleon-nucleon potential is shown by the red line. It has a shallow minimum of few megaelectron-volts at the distance of about 1 femtometer. At lower distances, this potential becomes strongly repulsive. Sakatons inside baryons are expected to be at distances much smaller than 1 femtometer. So the repulsive Sakaton-Sakaton interaction is going to add large positive contribution to the total mass. The overall stability of the compound system now depends on a delicate interplay between attractive green and repulsive red forces. If the repulsive force wins, then this Sakaton group will spontaneously dissociate into a neutron and a pi plus meson, or a proton and a pi zero meson. As we will see below, this is exactly what happens in our version of the Sakata model. This particular combination of Sakatons is a nuclear resonance with a very short lifetime. So, in order to move forward, we are going to build a more detailed model of interactions between Sakatons. And this is the main topic of my presentation today. First, for more generality, I will add a fourth Sakaton to the mix. This is a real existing charmed lambda particle with a charge of +1. I believe this model can be extended to cover also the beauty and truth quantum numbers, but we will not do that. Any system of n Sakatons will be described by the following Hamiltonian. The first term is just the sum of the rest energies of the Sakatons. The second term is the sum of their kinetic energies, and the last term is the sum of pairwise interaction potentials. The interaction potential between two Sakatons is the sum of three Gaussian functions. Thus, for each pair, we have 6 interaction parameters whose optimized values are shown in the table. I'm showing you this table very briefly, but you have to realize that fitting these parameters took 99% of the entire work effort. Looking at this Hamiltonian, you can easily notice that my model has a number of severe limitations. First, I'm using a non-relativistic quantum theory. Second, I completely ignored interactions that depend on particle spins, though it is well known that they play a significant role in subatomic interactions. So in the best case, we can hope to reproduce only some gross features of the particle zoo inhabitants. And we are not pursuing precise agreement with experiment. Let me now show you how the Sakaton potentials look like in real space. For comparison, the two gray lines here show two well-established potentials between nucleons. They are known to reproduce the properties of atomic nuclei pretty well. As expected, these potentials have a rather shallow minimum at the distance of around 1 femtometer, and they become strongly repulsive at shorter distances. Our optimized Sakaton-Sakaton potentials are shown by full black lines. They differ from the traditional potentials in two aspects. First, the minimum is shifted to larger distances, and second, the potential well is somewhat deeper. The black dashed line shows a characteristic Sakaton-anti-Sakaton potential. It is almost a mirror image of the Sakaton-Sakaton potentials. Instead of the potential well, there is a hill at about 1.5 femtometer. And at smaller distances, instead of repulsion, there is a strong attraction responsible for the Fermi-Young Sakata type binding. What is good about the Sakata model is that it's almost free of arbitrary assumptions. It follows almost effortlessly from the known experimental facts. The first fact is simply undeniable. The proton, neutron, lambda, and charmed lambda particles do exist in nature. So one simply cannot doubt the existence of Sakatons. Second fact, with high certainty we know that Sakaton-Sakaton and anti-Sakaton-anti-Sakaton potentials are highly repulsive at short distances, where it matters for the meson and baryon structures. There is less information about Sakaton-anti-Sakaton interactions, but a lot of indirect evidence points to the attractive nature of these potentials. Finally, let us accept the specific form of the Hamiltonian and see what kind of species we'll get in our particle zoo. In this journey, we'll be helped by two computer codes. One is called FBS. It realizes the stochastic variational method of Varga and Suzuki, and it provides very accurate ground state energies for any group of up to 5 Sakatons. The radial code handles two Sakaton species. Excited states and scattering amplitudes are also available in these cases. So, welcome to the particle zone. We start our trip at the meson park. First, let's look at mesons consisting of a nucleon and an antinucleon. The corresponding attractive potential has four bound states as shown on the left. The diagram on the right compares these states with experimental data. Multiple meson states found in nature are shown by hatched boxes. The qualitative agreement is reasonable, apart from the fact that our model predicts only two S states, while there are three such states in the real world. For lambda anti-lambda states, the agreement is not so good. Only two states are predicted by the model, one S and one P, but there are four states in nature. We are doing a better job for lambda anti-nucleon mesons. The model missing only the F state whose mass is very close to the dissociation limit. Here are results for the mesons containing the charmed lambda particles. As you see, our model overestimates particle masses, but relative positions of the mass levels are in a good shape. The radial program can be also used to calculate total elastic scattering cross sections for some Sakaton pairs. The agreement is pretty good at low energies, but for higher energies the errors can reach one order of magnitude. Next, let's go to the baryon pavilion. This is the full list of baryons that are predicted to be stable in our model. Of course, the proton, neutron, lambda, and charmed lambda should be excluded from this list because they are the elementary Sakatons. All other baryons shown here are stable bound states. Most of them have two Sakatons and one anti-Sakaton, as in the basic Sakata model, and their predicted masses are in a reasonable agreement with experiment. But there are also two examples of pentasakatons that are shown in bold. Actually, if you decide to build all possible combinations of three sakatons and two anti-sakatons, you'll end up with 170 such particles. But it's remarkable that 168 of such species are found unstable in our model, but the only two stable combinations corresponds to real particles found in nature. I have also found that all 123 tetrasakaton species are unstable. So it is very important that our model not only predicts particles that do exist in nature, but it does not predict non-existing particles. This can be seen clearly on the next slide. The table here lists 7 baryons which have a definite quark composition. Experimentally, these states either do not exist or have very short lifetime. This correlates well with our model, which predicts this species to be unstable. Next, let us take a walk along the shore of the nuclear lake. There are hundreds of stable and not so stable nuclei in nature, but unfortunately our theoretical methods will allow us to explore only the lightest members of this family. Here is a full list of isotopes and their calculated binding energies. They are in reasonable agreement with experiment. There is only one major qualitative discrepancy. We predicted a stable configuration of 4 protons and 1 neutron that does not exist in nature. Finally, we also investigated so-called hypernuclei, in which one nucleon is replaced by the lambda particle. We managed to confirm the stability of 3 known hypernuclei, but one of them, unfortunately, was found unstable in the model. These are my conclusions. First, I think that the Sakata model is attractive because of its simplicity and the minimum number of arbitrary assumptions. Second, its predictions for the stability of mesons, baryons, nuclei, and hypernuclei are qualitatively correct, despite using very crude approximations for the Sakaton potentials. Can Sakata model become a realistic competitor to the quark model? More studies will be needed to answer this question. More details about this work can be found in a preprint at this address. And I would like to thank wikipedia.org for the portraits and images, and you for your attention. Thank you.